Let's build another toolbox. This one will be a summary of equations that we introduced in Chapter 3 of our study of engineering thermodynamics. The first thing we did in this part of our studies was introduce saturated mixtures. And a saturated mixture consists of two components. It's saturated liquid and saturated vapor. And to define the state of a saturated mixture, we need to determine its quality. The quality is defined as the mass of the vapor divided by the mass of the liquid plus the mass of the vapor. And of course, this denominator represents the total mass because saturated liquid and saturated vapor are the only two components in a saturated mixture. So we can write that the mass of the saturated vapor is just the volume of the vapor divided by the specific volume of the saturated vapor, V sub G. We could also write that the mass of the vapor is the quality times the total mass. The mass of the liquid is the volume of the liquid divided by the specific volume of a saturated liquid, V sub F. We can also write that the mass of the liquid is just 1 minus the quality times the total mass. And we can also write the total mass is the total volume of the mixture divided by the specific volume of the mixture. We can calculate properties of a two-phase mixture knowing the quality, and I've demonstrated that with specific volume, but it works the same with other properties, for instance, internal energy, enthalpy, and entropy. We can say that the specific volume of a saturated mixture at some quality X is just V sub F plus the quality times V sub G minus V sub F. And if we have the specific volume and want to determine the quality, we can say that the quality is just V minus V sub F over V sub G minus V sub F. We introduced a new property, enthalpy, which is just the internal energy plus the pressure times the volume. So H is U plus PV in terms of energy. If we do everything in terms of unit mass, we use small letters, in which case enthalpy, or the specific enthalpy, is equal to the specific internal energy plus the pressure times the specific volume. We introduce constant specific heats. For gases, we have two specific heats, C sub P and C sub V. And we can use C sub V to determine delta U during a process. That's equal to the mass times C sub V times delta T. The change in enthalpy during a process is the mass times C sub P times delta T. And we also have a value K, which is the ratio of specific heats. It's C sub P over C sub V. Sometimes known as gamma, but almost always referred to as K. And we have some relationships between the specific heats and the gas constant R. C sub P minus C sub V is equal to R, so we'll notice that C sub P is always larger than C sub V. And C sub P is Kr over K minus 1. C sub V can be determined as R over K minus 1. We also introduced the ideal gas law, which we can write as pressure times volume is nRT, where n is the number of moles and R sub U actually is the universal gas constant R. We can rewrite this as pressure times volume is mass times a specific gas constant for the gas of interest times the temperature, where the gas constant R is just the universal gas constant divided by the molecular weight of the gas. We can divide both sides by mass and we get PV equals RT, or V is 1 over rho. We can rewrite the gas law as pressure is rho RT. Now the universal gas constant in SI units is 8.314 kilojoules per kilomole K. The universal gas constant in English units is 1545 foot-pounds force per pound mole degree R. Now, when an ideal gas is used in a closed system, both the mass and the gas constant are constant, and that allows us to write this expression of ratios, which is essentially PV over T is a constant. So P1 V1 over T1 is going to equal P2 V2 over T2. And when we have polytropic processes, and we recall that a polytropic process is just PV to the n power is equal to a constant, and n can take on any number between 0 and infinity. That is to say then, because it's a constant, that P1 V1 to the n power is P2 V2 to the n power. And work done by a polytropic process when n is not equal 1, the work is the integral from V1 to V2 of P to V, which we can solve as P2 V2 minus P1 V1 over 1 minus n. Now when n equals 1, the work for a process taking place between state 1 and state 2 is just P1 V1 times the natural log of V2 over V1. Let's summarize equations of interest for various processes, all of these involving an ideal gas. So here's what we know about an ideal gas that takes place in an isobaric process. That's a constant pressure process. We can write the gas law as V1 over T1 is equal to V2 over T2. We can write the energy balance as delta U is Q minus W. But work in a constant pressure process, and remember in a constant pressure process, it's a polytropic process with n equals 0. We can write that the work is the pressure times V2 minus V1. And the heat transfer can be written as the mass times C sub P times T2 minus T1. If we have an ideal gas in an isovolumetric process, this is where the volume is constant, we can write the ideal gas law as P1 over T1 equals P2 over T2. And energy balance is simply that delta U is equal to Q. No work can be performed in a constant volume process. And this is a polytropic process with n equals infinity. And we can find Q as the mass times C sub V times T2 minus T1. If we have an ideal gas in an isothermal process, that's a constant temperature process, we can write a polytropic process as P1 V1 equals P2 V2. An isothermal process, n is equal to 1. So this is really PV to the 1 power. Our energy balance becomes that delta U is equal to 0. Therefore, Q is equal to W. And work is simply P1 V1 times the natural log of V2 over V1, which can also be written, because it's an ideal gas, as the mass times the gas constant times the temperature times the natural log of V2 over V1. Now, if we have an ideal gas in an adiabatic process, remember an adiabatic process is one in which the heat transfer is 0. Then we can write an energy balance as work is equal to minus delta U, where delta U is mc sub V times T2 minus T1. We can also write delta U as C sub V over the gas constant times P2 V2 minus P1 V1. Remember, in an adiabatic process, it's a polytropic process with n equals K, where K is the ratio of specific heats. And we can write this as T1 V1 to the gamma minus 1 power is equal to T2 V2 times gamma 1 minus 1 power. And gamma here is simply used to represent the value of K. I'm not certain why our textbook uses both, but gamma here is just K, which is the ratio of C sub P over C sub V. Another expression that can be written for this particular situation is P1 V1 to the K power is equal P2 V2 to the K power. We can write certain equations of state for a polytropic process involving ideal gases. They are that T2 is to T1 as P2 is to P1 taken to the n minus 1 over n power. That's also equal to V1 over V2 to the n minus 1 power. Another equation of state would be that P2 divided by P1 is equal to T2 over T1 to the power n over n minus 1. And remember, this is an ideal gas being used in a polytropic process. Now, when n is not equal to 1, we've previously calculated the work for a process 1, 2. It's the integral from V1 to V2 of P to V. And for an ideal gas, we can solve that in multiple ways, but I'm introducing a new one here. It's the mass times the gas constant times T2 minus T1 all over 1 minus N. Now, if N is equal to 1, that work term is P1 V1 natural log of V2 over V1, or we can write that mass times the gas constant times the temperature times the natural log of V2 over V1. We can also write it as the mass times the gas constant times the temperature times the natural log of P1 over P2. We also introduced a compressibility factor, Z, which we can insert into the ideal gas law to calculate either temperature, pressure, or specific volume for a gas when we don't have tables that we can use. So if you recall how we did this, if Z turns out to be 1, well, then we have an ideal gas and we use the ideal gas law. But if Z is not equal to 1, then we will write that pressure times specific volume as ZRT. And Z comes from the compressibility chart, and the two variables that we use to enter the chart are the reduced pressure, which is the pressure of the gas divided by its critical pressure, and we use the reduced temperature, and that is equal to the temperature of the gas divided by the critical temperature.